Everyone, today I will be presenting on Baire's theorem. So Baire's theorem is that the set of real numbers cannot be written as a countable union of no or dense sets. And with this, we're going to do exercise 3.5.10. And this is really just a proof by contradiction where they want us to assume that e sub 1, e sub 2, e sub 3, and so on are each no or dense and satisfy that the real numbers are equal to the union of e sub n. So first I want to get into some helpful definitions and theorems we'll be using within the presentation. The first one is theorem 3.5.2, and this is from the textbook, and it states that if G sub 1, G sub 2, G sub 3, and so on is a countable collection of dense open sets, then the real numbers are equal to the intersection of G sub n is not empty. And then definition 3.2.11 is also from the textbook, and it's given set A is a subset of the reals. We let L be the set of all limit points of A. Thus, the closure of A is defined as A bar, which is really just the union of A and L. And then from the textbook again, we have definition 3.5.3, and this is says a set is no or dense if E bar contains no non-empty open intervals. And then this isn't a formal definition from the book, but it features, this is a set complement. And it says, given a set A is a subset of the reals, the complement of A refers to the set of all elements of the reals, not an A. So now we're going to start our proof. First, we know that if set A is a dense subset of the reals, then every point of the reals will be a limit point, and then we can make the claim that A bar is in the reals. We also know that if a set B is a no or dense subset of the reals, then B bar contains no non-empty intervals. And these are both from definitions we just talked about. So now we're going to take E sub 1, E sub 2, E sub 3, all the way to E sub n, such that all E sub I are no or dense in the reals, and then it satisfies the real number is equal to the union of E sub n. So by definition 3.5.3, the real numbers are equal to the union of E bar sub n, and this is no or dense. So now we need to prove that E bar sub n is countable. So to do this, we're going to find the intersection. And to find the intersection, we're going to apply De Morgan's law. And this is just a law that relates unions and intersections of sets through using the complement. So we're going to take the complement of the real numbers, and this will give us the intersection of E bar, or the complement of E bar sub n, is actually equal to the empty set. And we know this because the complement of the real numbers is the set of all elements not in R. And we know that all numbers are real numbers, so this set is just empty. So because E sub n is nowhere dense in the reals, we know that the complement of E bar sub n is everywhere dense in the reals. And since E bar sub n is a closed set, because it contains the limit points, and we use definition 3.2.11 to know this, we can assume that the complement of E bar sub n is an open set. So while the intersection of the complement of E bar sub n consists of open sets, theorem 3.5.2 states that the intersections cannot be empty. But last side, we just said that the intersection of the complement of E bar sub n is empty. So here's the contradiction we came to. So therefore, the set of the reals cannot be written as a countable union of no or dense sets by proof of contradiction. And that is my presentation. Thank you for watching.